So I thought you all might have a revolt if I were to say I was going to do another Chica talk based on an earlier, come on, here we go. There we go. Based on the initial announcement that went out, some of you, I think, were expecting a talk on causal reasoning. In fact, I'm going to talk about causal reasoning, but I'm pretty sure, if anybody wanted to hear about causal reasoning, you can leave. In fact, I think Peter Schwartz decided not to come because I told him it wasn't causal reasoning, but I'm going to talk, I am going to talk casually about causal reasoning because I've been thinking about it in terms of being potentially a critical tool for the learning healthcare system as it's currently emerging. So I really have no disclosures to make. In one slide, I'm going to briefly mention the Chica system, in which I do have a financial interest, but I have no other conflicts of interest to report. This is basically going to be a book report with a few things added in at the end. I actually have not quite finished reading it. This is the same thing I did in middle school. You know, I give a book report on a book I hadn't finished. But I want to talk about Judea Pearl's new book called The Book of Why, The New Science of Cause and Effect, because I think it's relevant. I'm going to quote verbatim two passages from this book that kind of caught my attention. The first one is from Dr. Pearl himself. He said, unfortunately, statistics has fetished this common sense observation. It tells us that correlation is not causation, but it does not tell us what causation is. In vain, you will search the index of a statistics textbook for any entry on cause. Students are not allowed to say that X is the cause of Y, only that X and Y are related or associated. That rings a little bit true. I think most people have heard that at some point in their statistical training. And then the second one, he quotes a political blogger who wrote this, which I thought was kind of interesting. You see it all the time in studies. We controlled for, and then the list starts. The longer the better. Income, age, race, religion, height, hair color, sexual preference, CrossFit attendance, love of parents, Coke or Pepsi. The more things you can control for, the stronger your study is, or at least the stronger your study seems. Controls give the feeling of specificity, of precision, but sometimes you can control for too much. Sometimes you end up controlling for the thing you're trying to measure. So these are a couple of very specific examples of where you wouldn't want to control for a variable. And as I read that last quote, it dawned on me, I give this completely insufficient thought when thinking about an analytic plan for a study. So let's suppose that you're trying to ascertain the effect of X on Y. And you have Z in between. Z is a mediator. Right, so X influences Z, which in turn influences Y. Well, if you control for Z, poof, the effect of X on Y goes away. And even a little bit subtler than that is number 2 up here, where X's effect on Y is mediated through M, but M also influences a variable Z. If you control for Z, it has almost the same effect, maybe not quite as strong because the relationship is not perfect. So this is a kind of gruesome example of a causal diagram that Dr. Pearl puts in his book. He says what's happening here is a court order is given to a captain, and a captain gives the 2 shooters on his firing squad an order to shoot the prisoner, and the prisoner dies. So this is a causal model. Each event causes the next one. And one of the things that lends a lot of power to causal models is that you can postulate about what would happen if you influence the of shooter A decides, well, I'm just going to shoot the victim anyway, right? Now there's suddenly none of the rest of this matters. Like before, I could say, oh, the prisoner died, and if this model held true, I could work my logic all the way back up to say, well, the court must have found him guilty. Here, that that chain of reasoning is broken because the victim will be shot either way. I could also propose that shooter A decided not to shoot the victim and say, well, what does that mean? Well, it turns out in this case, it doesn't matter because there's a shooter B, right? Which he would argue is why we have firing squads instead of individuals firing. All right, so that's a causal diagram. These are not entirely new. This is a causal diagram describing what happens when you try to mate guinea pigs to obtain a certain coloration in them. And it was, I'm not going to walk you through the entire thing. I mostly just wanted to dazzle you. This is from a publication in 1920. But what's shown here is a causal diagram developed by Sewell Wright, and he was able to use this and the experimental data he had to show that heritability only affects 48% of the coloration, and most of the rest of it has to do with developmental events that happen in the womb. And he did that by measuring all of the measurable relationships between the causal arcs that he put in there, and then controlling for those, he was able to show that the residual effect was 48%. This is another experiment he did that is maybe a little easier to understand. There was an observation that there was a certain amount of additional weight that guinea pigs gained, depending on how long, you can tell he studied guinea pigs, depending on how long they remained in gestation. So the question was the duration of the duration of the gestation period has an influence on the weight of the baby, the pup, but he argued that, well, also the size of the litter seems to have an effect on the size of the pup, and the prenatal growth rate of the babies is also influenced by that. So what he found was this sort of triangle of causation. And he had to control for 3 of those things to figure out the true value of P, the relationship between the duration of gestation and the size of the pups, which turned out, by the way, to be quite a bit lower than people had thought it was. All right. So in order to understand how these causal diagrams get analyzed, we have to think about 3 different ways that variables can interact with one another in a causal fashion. And this is the first one. The example here is that we have fires, we have smoke, and we have a smoke detector, an alarm system, right? Most alarm systems are based on smoke particles, right? So the fire produces smoke, and the smoke sets off the alarm. But if we could somehow pull all the smoke out of the room, and the fire would not set off the alarm. So the alarm, the association between fire and alarm is conditional independence. The alarm is conditionally independent of the fire given the presence of smoke. So if smoke is absent, fire and alarm are independent. If smoke is already there, fire and alarm are independent. They don't help you if you stratify for the presence of smoke. The second one is called a fork. This one is called a chain, right? And this is where mediators come into play. This one is called a fork, and it illustrates what we usually think of as confounding. So shoe size turns out to be highly correlated with reading ability among children. Seems ridiculous, right? But it is not, that relationship goes away if you control for the age of the child, right? And that's because the age of the child affects both the shoe size and the reading ability of the child. Right, so that's if you take that away, then the association goes away. So that's a fork. The third one is kind of an interesting one. It's called a collider. And colliders lead to a lot of confusion. I'll show you an example that is near and dear to my heart that he brought up. But this example is that both talent and beauty can lead to someone becoming a celebrity. Either one. So if you're a celebrity, that likelihood of becoming a celebrity is influenced separately by talent and beauty. Okay, and let's say either one of those is sufficient to get you celebrity. So what that means is that if you control for celebrity, let's say we take a stratum of celebrities, we take all the celebrities and we look at the association between talent and beauty, they will appear to be negatively associated with one another, because if you've got talent, that's enough to make you a celebrity, and you're no more beautiful than anybody else, right? On the other hand, if you have beauty, then you can become a celebrity, and you're no more likely to be talented than anybody else. So by controlling for a collider, you actually can take two things unrelated and make them appear to be inversely related. So these are the three things. This is called in the DAG world, the directed acyclic graph world, which not as a causal model necessarily, but I'm very familiar with because of Bayesian belief networks. This is called deconnection or deseparation. In other words, in the connected group, if you don't control for the variable in the middle, then the mediator connects A and C. This is in your middle column there. The mediator affects A and C. The confounder will connect A and C, but the collider does not connect A and C. They are not connected. They're separated in the presence of that. But if you control for the middle variable B, then A and C get separated in the first case, separated in the second case, but they become connected if you control for a collider. All right. So this is, let's make a deal. This is the one that's near and dear to my heart because it's one of my very favorite paradoxes out there. And anybody who has sat through one of my lectures has heard it, although you've probably heard it in other places as well. So I don't know, how many people remember the Price is Right TV show? Yeah, with Monty Hall, right? So the Monty Hall problem is you've got three doors. One of them has a car, a fabulous prize, and the other two have goats. And you pick at random, or by whatever heuristic you use, one of the doors to see whether it has the prize. And Monty Hall proceeds to show you one of the other doors. The one he shows you is always one of the ones that has a goat. And then he asks you, do you want to stick with the first door you picked, or would you like to change doors? And the question is, what should you do? Should you switch doors? Should you keep the door you picked in the first place? Does it make any difference? I'm actually kind of curious. How many people think that you should definitely switch doors? Okay, pretty good. How many people think it doesn't make any difference whether you switch doors or not? All right. Turns out, and I don't have time in my very brief talk right now to explain why, although I'll be happy to talk your ear off. It turns out that it is always better to switch doors. Your chances of winning go from 1 in 3 if you stick with the door you picked to 2 in 3 if you switch after Monty Hall shows you the door. And there are a lot of explanations for this. This one I thought was kind of clever. Which door Monty Hall decides to open is determined by two things: the door that you picked and the door that has the car behind it. So which door has the car behind it influences which door he opens, and therefore there's information in that. And we all sort of think of the problem this way, as if that didn't exist. That's why your temptation is to think, oh, it doesn't matter whether I switch or not, because you're forgetting that which door the car is behind is one of the determinants of which door he opens. And that's a collider. And so Judea Pearl would argue that this is another example of how we're not very good at handling colliders. All right, so basic confounding is pretty straightforward. If you've got a fork like Z influencing both your predictor X and your outcome Y, you have to control for it. So for example, a study looking at walking and mortality, showing that vigorous walking reduces mortality. You have to control for age because age can influence both of those things. We think of this as like a randomized controlled trial. This is a causal diagram for a randomized controlled trial in which you force people to walk or not walk. Unfortunately, we can't usually do that. And so we look at this as This is called a backdoor adjustment, where we look at the fork and the fork creates what's called a backdoor because it has a backdoor into walking as well as influencing mortality. So if we control for it, we get rid of that backdoor and we can look at the true relationship between walking and mortality. Here's an example of a sort of trickier one. Supposing we want to look at the association between X and Y. Which of these variables, A, B, C, and D, and E, do we want to control for? It's not trivially easy, although I will point out how we can tell. We actually don't need to control for any of them. In fact, we don't want to control for any of them. Because although on the surface it looks like there might be a backdoor to E and that would influence Y and therefore we'd have a problem, in fact, they're connected by a collider, B. So if you controlled for B, or for that matter, if you controlled for either B or C, you're going to eliminate a collider and cause a relationship to exist between X and Y that might not otherwise be there. So the fact is you don't want to control for any of those variables or it will give you an incorrect model. Now, I have to say that one of the important aspects of this, which I didn't say up front, is that this assumes that you have a meaningful causal model of the way the world works. And so one of the objections you will hear, and Judea Pearl largely blames this on Carl Pearson, who's considered the creator of mathematical statistics. But Carl Pearson, I think his objection would be, well, how do you really know that this is the way these variables are associated with one another? I think that's a philosophical argument, so I'm not going to get into it. But it has caused a lot of problems. So for example, smoking and cancer. There was obviously a long political delay in smoking and cancer, and convincing the government to put warnings on all the cigarette packs and so forth. But the argument that was used is, well, how do you know there isn't a smoking gene that is associated with both the tendency to smoke and the tendency to get cancer? Right? That could be there. You have no way of proving it isn't. In fact, Fisher, of famous statistic fame, argued this vehemently. And of course, the tobacco companies loved it. But at the time, they were not doing this kind of causal work. I'll show you how sort of a causal framework might have solved this problem. But what they did is they said, well, let's suppose that everything was explained by a causal, by this confounder, this smoking gene. Well, the fact of the matter is that, the association between smoking and cancer is 9-fold. So you're 9 times more likely to get cancer if you smoke than if you don't smoke. That means that there would have to be a massive separation. So it's called Cornfield's inequality, because Cornfield made the argument about it. But it means you would have to have a massive difference between the prevalence of the gene in the smoking group versus the non-smoking group to explain its effect. In fact, if say 12% of the non-smoking population had the gene, it would be impossible to explain it, because 9 times that many people goes over 100%. So that was the argument that statistically won the day, was Cornfield's inequality. Along with that, there are a set of criteria called Hill's criteria. These are 5. There are actually 9, but one of these I found different sources, and one of these kind of combines 2 of the other ones. But it's kind of useful to think about in terms of whether you want to ascribe causality. And this is out of the 60s. This came out of the smoking and lung cancer debate. But you want to make sure that you have consistency of the relationship across different populations and showing similar results. You want to have a strength of association. And ideally, you also have a dose effect curve where more exposure to the cause results in a stronger effect. You want specificity of the association, like smoking and lung cancer. You don't want like smoking and lung cancer and diabetes and heart failure. And although interestingly, smoking through its many mechanisms probably does cause a lot of those. You want a temporal relationship, right? the smoking precedes the lung cancer. If you get lung cancer before you take up smoking, that's not very compelling. And you want coherence. That is to say, there has to at least be some kind of biological credibility or even some consistent laboratory research. All right. So what would be a causal diagrammatic way to address this same question? Well, one thought would be if you had an intermediary variable between smoking and cancer, for example, that you could measure. So the challenge here is we can't control for the smoking gene, or at least you couldn't in the 60s, because there was no, the technology to measure that in the population wasn't there. These days we could probably do it. But if you have an unobserved potential confounder, how do you handle that? And one possibility would be, let's suppose you had some independent measure of the mechanism by which smoking led to cancer, like the accumulation of tar in the lungs, and you could measure the accumulation of tar in the lungs. Then you can calculate the strength of association between smoking and tar, because there's a collider at cancer. And so the smoking gene can have no effect on that association. Now, I'm leaving out there, you could argue that there was an arc between smoking and the tendency to accumulate tar in the lungs. But if you can credibly say that doesn't exist, then you can make this argument, because the collider protects that association from confounding. And then secondly, you can look at the association between tar and cancer, because you can control for the observable smoking. And now you have two formulae that you can combine together to look at the true association between smoking and cancer, controlling for the smoking gene without ever invoking the smoking gene at all. So so committing yourself to a causal structure does give you a lot of strength in terms of the way that you can handle unobserved confounding. This is another example. Anybody who's done any work in public health knows who John Snow is. In London, he's famous for pulling the handle off of the Broad Street pump, which was contaminated with cholera and saving countless lives. Interestingly, he was very committed to this notion that the purity of the water was what mattered in cholera. But his contemporaries thought it was this thing called miasma, and poverty and impoverished conditions, and they sort of thought if it smells bad where you live, you're going to get cholera. Now that's probably a spurious, well, we know now that's a spurious association because it's mediated through water purity, but it wasn't known at the time. What he did, though, that most people don't know, is he did shoe leather epidemiologic work and studied the way water was supplied to London at the time. And the water came from two companies, the Southwark and Vauxhall Company and the Lambeth Company. And the former got their water from the Thames downstream from London. So it was tainted with sewage. And the latter got their water from upstream of London, where the water was not contaminated. But the two companies supplied water indiscriminately to the same sets of neighborhoods. So he could go individually from place to place. And this allowed him to do the following. Now, this is called an instrumental variable, and this is the causal diagrammatic representation of an instrumental variable. And I promise there's lots of people in the room who know more about instrumental variables than I do. But what you can do with those kinds of data are you can say, well, obviously the association between the water company and the water purity is that association you can make, because it's not confounded by miasma in this circumstance. Secondly, you can look at the association of the water company and cholera, because those data exist, and you don't have to worry about confounding because the water company and cholera are not confounded by this unseen miasma, and so the ratio of those coefficients that link those two things together will tell you the association between water purity and cholera. Okay. Oh, I guess I should say, and that's because miasma is a collider with the water company, and so it can't confound. In fact, it has to be there. All right. So I just want to close by mentioning we have done a little bit of work along these lines. So this is a belief network model that I actually made up based on, I have to admit, it's not quite causal. There are a couple of arcs in there that you would have to say those are not causal, but it was largely causal, and it was a domain expert, calling myself an asthma expert, model of the problem is that kids who have wheezing before the age of 2, which is a condition called bronchiolitis, and it's caused by viral infections, are at increased risk for developing asthma after the age of 5. But we wanted to see if there were certain things in their history that would be a stronger predictor of them getting asthma by the time they turned 5. And so I built this model to connect the variables that we had to look at. This is one that we used a product that I think is still out there. It's a free product from Windows called WinMind, which is a greedy algorithm for building Bayesian belief networks from raw data. And so we had the computer build this one. This one clearly has some kind of oddball associations, like in this model, taking an asthma drug and having eczema and your insurance category all caused your race to change, right? So obviously that if you tried to interpret this as causal, it would be wrong, right? It's not causal. This is just probabilistic. So this is just pure association, no causality. So we decided this was just something I was curious about, is if I learn something through this greedy machine learning algorithm, will it behave differently from one that I developed on my own? And these are 2 ROC curves that we used to look at that. And the first one uses the same data, which actually came from Eskenazi Health many years ago. The first one shows that they basically overlap, the ROC curves for predicting whether or not the kid would go on to get asthma completely overlap. But then we applied it to a different set of data that we got out of the Chica system. And as you might expect, you go to a different data set, it doesn't perform quite as well. But we saw a bigger decrement, not gigantically different, but a slightly bigger decrement in the mind non-causal model than we did in the expert derived model. So that's a little mild evidence in favor of doing this. One of the other appealing things about this, and this is just, I am not even going to try to get you to understand or explain all of this, but there are, you will see there, the kind of highlighted nodes represent sort of the usual sampling and assessment observed variables through an epidemiologic study. And what this came from we actually reproduced this in a paper that Harold Lehman and I recently published in Learning Healthcare Systems. And what it depicts is that you can look at all of the biases that have been described by epidemiologists through the years. There's some kind of nice compendia of those, and show where you could build adjustments for all of those biases directly into the model. Now, in a real model, it's unlikely you try to get all of these, but it serves the principle of saying that this format, this causal network format, can allow you to build in controls of that sort as well. And then finally, this comes also from the Learning Healthcare Systems paper that we just published. This is a Bayesian belief network, but you'll see we've added a couple of different things there. In addition to the random variables, which are the ovals in there, there is a square decision node, and in the far right, there's a value node. And so I've converted this into what's known as an influence diagram, which is actually a decision model. So that if you can take a causal network and add in these features, and it actually converts it into a decision tool so that you can drive decisions. In fact, we have a little comparison between that and the algorithm you could derive from it. And so the pitch that we were making in that paper is that this ought to be the artifact that we generate and share on the in the learning healthcare system. This should be the knowledge artifact, because with all of these kinds of adjustments, you can decide whether it fits your environment or not, and you can adjust it to your own population. All right. So what's my recommendation before undertaking any study, experimental or especially observation? Construct a conceptual model of how you think the world works. Use a structural causal framework to do that, and analyze that framework using deconnection and deseparation to identify the deconfounders, the things that can take the confounding out of your model. So impose, and the reason that causal networks are useful in the learning health system is they impose a causal structure that creates a way to deconfound data and estimate causal effects. Kind of emulates an RCT in that regard with observational data. And it can make more robust predictions. Also, causal graphical models can be expanded into influence diagrams that directly supports clinical decision-making and adjusts to local conditions. And all of this makes the assumptions that you're using in your model explicit for sharing knowledge artifacts. With that, I'll stop, ask for, we're about out of time, but questions, discussion, or certainly complaints for anybody who thinks I'm being too radical here.
Time for one or two questions.
Okay.
So I was at a session at PAS last year, 2 years ago, and they went over some causal diagrams, and they mentioned how maybe they were having some difficulty in using causal diagrams in their manuscripts when they submitted for publication and review. They were getting pushback of, why aren't you doing the traditional controlling for this, and this? And they were trying to, and I didn't know if you had any experience or thoughts on how to defend them as sound reasoning for your models to a more traditional audience.
Yeah, I agree. That can be a real problem. It's the first thing I would say is, you know, if you're doing something that is a little outside of the norm and requires a level of knowledge of the mathematics that you're doing underlying it, you're going to meet that resistance, because there are too many people out there who are interested in the thing they're studying and not that interested in the biostatistics. You know, they hire a statistician. The statistician says, well, you can do it this way. And then if you say, well, I did a regression analysis, a logistic regression analysis to control for all these variables, everybody says, oh, well, then you must have done a good job, right? Whereas if you do this, they go, I don't know what the heck you did. So that's a problem. That's the first thing I'd say. I will say that there are some standard, that the graphics makes it easy to figure out what you need, relatively easy to figure out what you need to control and what you don't want to control. But there are structural equations out there, and structural equations, although they're not always used this way, structural equations are really intended to do the same thing. They assume a certain relationship among the variables. And so another way to do this would be to use a causal diagram to decide what's the structure of my problem, what am I going to control for, and then convert that into structural equations. And then say you're using structural equations, and people say, oh, well, that's in my statistics textbook, so it must be okay.